In this video we're going to take our look into electromagnetic induction a step further by looking at Lenz's law, but to do that we first of all need to just refresh our memories about the previous video. So a couple of points to note there. The first one is that an EMF will be induced between the ends of a conductor, and that will only happen when there is relative motion between the conductor and the magnetic field. And I'm just going to add in brackets here the word perpendicular. We'll get onto why this idea of perpendicular motion is important in a coming video, but just to alert you to that here. So motion between the conductor and the magnetic field. So that EMF is always going to be induced, whether that conductor is connected to anything else or not. The EMF will be induced between the ends of the conductor. That's due to the separation of the charges, positive and negative, between the ends of the conductor. Second thing then is that current will only flow when there is a closed circuit, or if the conductor is connected to a closed circuit. And the closed circuit that we had in the previous video incorporated a resistor. It doesn't really matter what that closed circuit is, so long as there is a path for current to flow through. And if there's no path for the current to flow through, then there won't be a current induced. When we're now looking at Lenz's law, we're specifically dealing with this idea about the current that flows. So we've got that an EMF is induced, and we'll deal with that in more detail in another video. Here we're going to look at the direction of the current specifically. So the direction of that current is summarized by Lenz's law. Now, the statement that I'm going to write here, it's actually it's a fairly simple way of stating this law. There's actually quite a lot to it, and we'll go through that in more detail as we continue to develop these ideas. The induced current it will flow in a direction such that it opposes the change that caused it. Now, what that means, we'll have a look at an example to identify that. And this, like I said, this does become much more complicated depending on the scenarios that you're looking at. We'll refer back to one of the examples that we looked at in class, and we'll deal with a north pole of a bar magnet entering a solenoid. And so imagine that we have a solenoid here with a number of turns around it. I'll just draw that in quickly. Just to make this a bit quicker, I only draw a few turns. So there's our solenoid, and we will have that connected to an ammeter so that we have a closed circuit that current can flow through, and a magnet positioned here with the north pole going into, so that's moving down with some velocity. Now, the first thing to note here is that the north pole of the magnet is entering first. And by dealing with the north pole, what we know about magnetic field lines is that they originate from a north pole and spread out as they come away from the north pole. Now they would loop back around into the South Pole, but we're only really interested in this region that's beginning to enter the solenoid itself. So we see that the current flow in the solenoid, let's say the current flow induced in the solenoid, in order to oppose that change that's causing the current to flow, that must mean that it's going to produce a north pole at the top of the solenoid. And when I say a north pole at the top of the solenoid, I should probably put that in inverted commas. There isn't really a north pole being produced there. It's more that the magnetic field lines that would be coming out of the solenoid here are going to be opposing the direction of the field lines coming in. So what that means is that the solenoid effectively looks like it has a north pole at the top and a south pole at the bottom if we were to compare it to a bar magnet. And the reason for that is that it's going to oppose the bar magnet's north pole coming closer. So that shows us then that the magnetic field produced by the induced current is going to oppose the motion of that bar magnet entering. So we can then use that to figure out the direction of the current that will flow, and that's going to be done by using the right hand grip rule for solenoids. And if you're not sure about what that is, you can refer back to subtopic 5.4. What that shows us then is that very briefly, fingers showing the direction of the current that will flow, thumb showing the direction of magnetic field lines inside the solenoid. So thumb would be directed up there, which means that your fingers would be curling over, and so the current's going to flow in this direction. So that would be our current there, which as we follow it through means that current will flow down through the ammeter. So there's one example of how to apply Lenz's law. As I said, these scenarios depend on what's moving, how it's moving, what the relative motion is. So very simple example to start with. We will develop that further as we look in more detail in the coming units at magnetic flux and magnetic flux linkage. There's one last thing to say about Lenz's law that is worth noting. And that is that Lenz's law is basically just an application of two ideas that you should be familiar with. The first is that it's basically just conservation of energy. And the second is that it's an example of Newton's third law. So for every action there's an equal and opposite reaction. We'll have a look at those in class in more detail, but just wanted to highlight that to you, that Lenz's law is not something new and different. It's just an application of those couple of ideas, or those principles or laws, and allows us to then just sort of link back to those ideas of conservation of energy and action and reaction forces.